Hello everyone, my name is Chaoshun, a postdoc researcher from the Ohio State University. Today I'm going to present our work on mobile game security, playing without paying, detecting vulnerable payment verification in native binaries of Unity mobile games. This is a joint work with my advisor, Professor Zhiqiang. In this work, we uncovered two important types of vulnerabilities in the in-game purchase of Unity-based mobile games. We have correspondingly developed a payment-aware static analysis tool to detect them and found about 9,000 games containing these vulnerabilities. So let's get started. In 2021, the video game market made 175 billion in revenue worldwide. Surprisingly, mobile platforms have become the largest segment of game industry, which generated 52% of global revenue. It is more than the combination of both PC games and console games. For a mobile game, there are several ways for monetization, such as pay-to-play, in-game advertising, and in-game purchase, which also known as IGP. In IGP, the developer offers digital products for users to purchase. Among them, IGP is the most popular one. To help developers implement IGP, Play Store provide SDK and APIs for faster implementation. However, game developers often use the wrapped SDKs that are provided by game engines. One benefit is that such APIs support cross-platforms, including Android and iOS. So how does IGP work? After the user clicks purchase, the game first initializes the payment request to the App Store. App Store processes the transaction by interacting with the user, and it will return the payment response to the game. If the transaction failed, it includes the reason. Otherwise, it contains the detail of the transaction, including the receipt, which will be used to validate the transaction. Then the game will send the transaction to the game server for validation and login. The game server can use the app-specific public key to validate the transaction signature, or it can send the transaction to the App Store for verification. After validating the transaction, the game server then distributes the digital products to the user. Obviously, it is critical for the game to verify the transaction at the server side. However, we found that some games implemented the IGP in the wrong ways. As shown in the picture, after receiving the payment response for the App Store, some games directly trusted the response without verifying the transaction. Since the mobile device is controlled by users, it is easy to hijack and modify the response in step 3 so that the payment can be bypassed. We call this vulnerability lack of verification. In another case, some game just verify the transaction locally. For the same reason, it is easy for an attacker to bypass the verification logic, such as making it always return true. We call this vulnerability local verification. Both implementations are vulnerable to payment bypass attacks. For the game that are developed with the different game engines, although the high-level steps are the same, the SDK and the implementation details are different. As such, in this work, we are targeting the most popular game engine. Our experiment on 300,000 games confirmed that Unity is the most popular one. It supports cross-platforms and offers easy-to-use IDE. The program language is C#. However, the compiling process is Euro compared to normal C# program. In particular, the C# code will be first compiled to assembles, which are also known as RL code. Then the RL code will be translated to C++ source code, and a standard C++ compiler will compile the code into native binary format eventually. The entire process is called RL2CP. It will make the game code secure and fast. However, it also makes the game hard to analyze. Let me show you some examples. On the left-hand side is the C# source code of the IGP processing code. The function named process purchase at line 3 is the recipient of the payment response from the App Store. The parameter in line 4 is the payment response. In the function, the game directly verifies the transaction at line 11 by using the app-specific public key, which is defined at line 7. Here is another example. It extracts the transaction receipt at line 6 and retrieved the corresponding signature at line 7 and 8. Then put it in an HTTP request, which will be sent to the server for verification at line 9. Next, let me show you the corresponding binary code. In our work, we use Ghidra to process the binary. The first part is the address and bytecode. The second part is the disassemble code. And the last part is the P code that is generated by Ghidra. We can see that each C# code has been translated to one or several native instructions and many symbols are missing. In this work, we handle the native binaries. So our goal is to identify the vulnerable IGP for the games that are based on Unity engine. Given a game binary, we want to identify whether its IGP is remote verification, local verification, or lack of verification. The first change is how to identify the vulnerable IGP. Our insight is to take advantage of system and Unity engine APIs. In particular, we first abstract the problem into a data flow analysis problem. By tracing the data flow of the returned transaction, if it flows to the network API, then we identify it as a remote verification. If it flows to a local validation API, it is local verification. All other cases are lack of verification. As such, for the shown example, the left one should be classified as local verification and the right one is remote verification. And the second change is how to pinpoint target APIs. As mentioned, the game binary doesn't contain any symbols. Without the symbols, we cannot identify the APIs. Our insight is that IL2CP actually packed the symbols of functions and classes into a separate file, which is required for the game binary. Because C# supports features like reflection, which needs symbols. As such, by analyzing the file, we are able to uncover symbols. For the last change, IL2CP has merged the system libraries and game code together. As a result, if we perform traditional data flow analysis, we have to analyze the system library when the game calls system APIs. It will make this analysis too complicated. Our insight is using API summary. In particular, we first summarize the propagation rules for the system and the Unity APIs. When we encounter such an API, instead of analyzing its code, we directly apply the rules. However, there is one indirect data flow often used in C# programs. As shown in the example at line 8, the code stored the receipt data in class field at line 4. This data could be used by other functions, which will lead to an indirect data flow. To handle such a case, our insight is to build a global class table. It indicates which fields of the classes are tainted and should be traced. As shown in the top right, it is a global class table. Please find more details in our paper if you are interested. With all those insights, we have designed and implemented Payment Scope, a static analysis tool based on Ghidra. At high level, it consists of 3 components: metadata extraction, which uncovers the binary symbols, payment-aware data flow analysis, and vulnerability identification. To test the payment scope, we have collected 2 million mobile apps from Google Play and found 10,000 mobile games that are developed based on Unity and supports IGP. The experiment took several almost 28 days. To our surprise, we found 8,000 games lack of verification and 721 games only verify the transaction locally. So this means more than 84% of tested games are vulnerable. To verify the experimental results, we have conducted FP and FN analysis manually. We applied the following rules to collect the sample games. In total, we collected 280 games. To confirm the vulnerability, we first use a virtualization tool to inject fake transactions into the game. Then we use a code patching to disable the local verification API. In the analysis, we didn't find any FP, and the FN is 29%, which means there are more vulnerable games. Please refer to the paper for details. To have a concrete understanding of the vulnerable games, we have grouped the tested games based on their install times. The polyline in the vulnerable is the vulnerable rate of each group. We can see that the vulnerable affects not only less popular games, but also super popular ones. Meanwhile, from the polyline, we can see that less popular games have a much higher possibility of being vulnerable, and the developers of popular games are more careful to secure their IGP. Then we group the games based on the game category. We can see that there are two types of games. Those vulnerability rate is higher or equal to 90%. A possible reason is that the games in these two categories are more likely to be a single player game, and these games depend less on the server. Having identified the vulnerabilities, we have made responsible disclosure to both Unity and the game developers. In total, we have contacted the 5,000 developers of the vulnerable games, and we have received hundreds of responses. Many developers promised to patch the vulnerability in the next version. And for the sake of time, I'm going to skip the limitation and the related work. So in summary, in this work, we presented payment scope, a fully automated system to identify vulnerable IGP among Unity-based mobile games. Our experiment shows that 84% of tested games are vulnerable. The source code of payment scope is available at GitHub. Please check it out if you're interested. And due to a family issue, I cannot join the conference in person, but my advisor, Professor Zhiqiang, will be there to answer your questions. Thank you.